Hello everyone. Today I want to introduce deep learning using ChatGPT. The idea is that I'm going to talk with ChatGPT about deep learning, and I'll try to show you how I would use it to learn about specifically deep learning and then more generally other topics. Now, of course, I prepared for this a little bit, but one of the problems with GPT, LLMs, large language models in general, is that they're not consistent. They will give different answers every single time. Whenever you open a new conversation, it will just give you a different answer. So that comes down to how you prompt it, prompt engineering. But I'm going to just go with the simplest thing I can think of on the spot, and then we can see how I would recover or I would add more information for it to give me information I'm looking for. And so I'm going to start with a very simple prompt. So we're going to open ChatGPT and start with a simple prompt. What is deep learning? So here I'm assuming you're already familiar with machine learning, linear regression, logistic regression, the basics. And I want to see if I can get it to introduce the topic the way I would do it if I were to design slides myself. So it starts with a very basic definition. It's a subset of deep learning, of machine learning, which is accurate, which is also part of AI. And it's using a neural network. This is essentially deep learning is, that's a very good definition of what deep learning is. It's just a neural network with more layers. We'll see what layers mean. And it extracts complex data. And of course, it uses these neurons, this neuron analogy, which I will try to get rid of this analogy for the next question. It goes through the different aspects. It has multiple layers. We'll see what these are. Large amounts of data, end-to-end learning, and it's optimized using backpropagation, right? Optimization, if you know about learning, machine learning in general, it's all about optimizing a model to find an optimal solution. And here we have something called backpropagation, which is not familiar if you haven't done deep learning before. Applications, that's also a very good aspect that should be covered, and it does it beautifully here, where we have image and speech recognition, natural language processing like ChatGPT itself, and autonomous driving, healthcare, and of course there's a ton of other examples. Now I wanted to introduce the mathematical theory behind deep learning also sort of briefly. And I will go back here, and I'll just copy a prompt that I've prepared and let's see what it gives me as an answer this time. So the question is, now introduce deep learning without alluding to the neuron inspired approach. Let's think of deep learning as a series of linear and nonlinear transformations, and introduce things starting from linear regression, then logistic regression, then neural networks, and then provide a very simple code showing an example of a neural network. Here I'll add do it in PyTorch just to make sure that it's using the right code I have in mind. And let's see what it gives us. Now, the problem, I think I've tried it a few times and it gives me slightly different answers every time. Let's see if this is going to be my favorite. So it does the introduction using y equals ax plus b in higher dimensions, where x is multiple inputs. And then it says for logistic regression, you simply pass it through this nonlinear function, 1 over 1 minus 1 plus e to the minus this complex w1x1 plus w2x2, this linear function. And then a neural network is essentially, it says the generalization is multiple layers of these transformations. So it passes through linear, applies a linear transformation, and then a nonlinear activation function. So a single layer neural network is simply two of these. So it calls this an activation now, which is what used to be the sigmoid function. It didn't introduce things the way I would, but let's go through it. And so then we have a wx plus b activation and gives us the next layer. And you have multiple of those layers, and it gives us these this simple code. So again, it's very good. I'm going to skip through a little bit, and just because I would like it to do it in matrix, can you introduce the topic in matrix form and highlight the form the function write the function as a composition of functions. Go a little more into the mathematical details. Okay, so I said matrix form, right? So I wanted to be a little more rigorous mathematically, a little less gimmicky. So instead of writing w1 x1 plus w2 x2, I wanted to tell me it's w times x, right? So already it started using bold letters, and it is stating the equation. So this is, again, it's y equals wx plus b. That's a linear transformation. Now it looks better. That's sort of more what I was looking for. And for logistic regression, it has this y hat equals sigmoid of wx plus b. And for a neural network, again, now it's simple. It takes an x. Sorry about that. I don't like this. Yes, so it takes an x. It passes a linear transformation to it, w1x plus b1, and then it applies a nonlinear function to it, f, which could be a sigmoid or ReLU, and gives me h. And then I pass an h times w2 plus b2, apply a g, a nonlinear function, and I get y hat. And it tells me what the dimensions are of w1 and w2. Much better. This is much more what I was looking for. A generalization of a deep neural network. So this is a neural network with one hidden layer, and it says, well, for a deeper network, it uses this composition type notation where the input is x, you pass it through a linear nonlinear function, which it's calling f1, linear nonlinear f2, etc., until it gets to g at the end. And here it talks about phi, wiz plus bi. This is the more general representation for layer I, for the ith layer. And this is very good. I think I'm satisfied. I'm much more satisfied now. Example of two hidden layers. Again, it does it twice instead of doing it once. So that's phi w1x plus b1, then phi w2 h1 b2, then some g. And I actually really like what it did with the g function, because what it's really doing is it's isolating the activation functions that are happening in the middle of the neural network from the last one, because the last one really depends on what your data looks like, right? If you are trying to predict some value between minus infinity and plus infinity, you'll probably use this. G will be just a unit, an identity function, or you can just get rid of it. If it's, again, some probabilities that have to sum to 1, then you'll use softmax, etc. And then it goes to, and creates a two-layer deep learning neural network. So here we have two layers. That's, you define a class. You also always don't forget to call NN module. Then it's a two-layer network. So you have a linear transformation that takes input size, then hidden size, and then another linear transformation, which is hidden size, then output size. And as you can see, this is a constructor. It's just defining the layers, which we haven't used them yet. These get used when you call a forward pass through the layer. And this is the general structure of how you would do it. The simplest way you would do it in PyTorch. So forward function is always called the forward function. It takes in the input and returns whatever the output is. So what it's doing here is it takes x, passes through the linear unit, then a rectified linear unit. This is not the only way to do it, by the way, in PyTorch. And you get the hidden layer, h1. Then you take the hidden layer, you pass it through the linear layer, and you get the output. And here specifically, it's using a softmax on the output. So it's taking the output and applying a softmax function. And finally, it's taking a two-layer, it's defining a two-layer neural network. As you can see, it's allowing for flexibility on how you define the architecture. So the input size, the hidden size, and the output size. And the input size is 2, the hidden size is 3, and the output size is 2. And it's defining some dummy data to just show how you can take in some sample input and pass it through to get the output. All right, so there's no training yet. This is just defining a two-layer network. And it goes through the explanation here, which is what I've just done. And then it has an explanation. So what's interesting here is that it hasn't really trained the network. It's done that before. So if we go back here, actually, it hasn't done that even here. Okay, so interesting. It hasn't done that. When I tried it before, it did do it. So great. Now, tell me how you would train a neural network on real data. Is it also gradient descent? Also, go through the mathematical details and tell me a brief code for demonstration. All right, so let's try this. And now again, it's sort of, that's what's coming on my mind. And again, even if you give it the same prompt, even if I had prepared the prompt, it will give me some different answer. So I'll just do it on the spot, and then we'll see. You'll see how I think about it. And sometimes I won't phrase things perfectly. You can do it better if you think about it a little more. Generally, it's better to give it more details, although that really changes with every version. Now that we have, for example, 01 with the more advanced version, it will simply plan things on its own. I can do that in a separate video, but here I'm using a model that you most probably have access to. So it's also gradient descent. It's stochastic gradient descent, in fact, and it involves also minimizing a loss function, that same thing that you would do in linear regression, and iteratively updating the model's parameters, weights, and biases. All right. So the gradient descent process is you minimize the loss function L with respect to some weights theta. Right. That's what we did in linear regression, in fact, and logistic regression. And here it's saying, well, we have to do a forward pass to compute the prediction given the input. So that's, you take the input, you get the output. We compute the loss, right, where here it's defining as the cross entropy. And it's assuming that you have multiple outputs. So it went with the assumption that it's a softmax. And finally, a backward pass, and that calculates the losses. And it's very important. It's a very good explanation. Computes the gradients of the loss function with respect to the network's parameters using the chain rule. It doesn't explain what the chain rule is yet. So we can ask it about this in a minute. And this is where backpropagation comes in. And it's a very important aspect of neural networks and how and why they work. And finally, we update the weights using the usual gradient descent update rule. And for a single layer, we have this input wx plus b times the activation function h. And it shows you one example of the chain rule, right? If we want to calculate the loss with respect, the derivative of the loss with respect to weight matrix W, we do dl dy hat dw. And so this is the kind of the simplest chain rule you'll get. As the network gets deeper, you get more of these terms to get, because it's a composition. Again, it's a function within a function within a function. So you'll get more of these derivatives chained with each other. And weight update, we update the weights, and code for training. So again, now it's defining a deeper network. So these are 3 linear layers. It's taking an image that's 28 by 28, and it's passing it through first 128 layer. So it flattens this. It goes to 128 inputs, then 64, then 10. And you can see this, how this happened. The view reshapes the input from 28 by 28 to a vector that is 28 times 28. Then linear, nonlinear, as we've done before, linear, nonlinear, right? So that passes x, gets back an x, and then passes the same x, gets back another x. This is something you can do in programming, right? That's not math. It's the same input that you're updating its value in place, right? So you don't have to use extra memory. And the last layer is simply a linear layer, and you get your x at the end fully transformed. Then it goes, it downloads the MNIST data set. This is a data set where it's written letters, written numbers, and it's supposed to identify whether it's any number between 0 and 9. So the output is actually 10-dimensional, and it will give you probabilities for each one of the outputs. This is the data loader. This allows you to, this is something I don't like about the interface, is that if it's a longer line, you can't really see it. So data loader, it takes in the training set, the batch size. This is the mini batches. You take 64 examples at a time, and you calculate gradients with respect to those. So it's somewhere in between stochastic gradient descent, where you just take one example at a time, and batch gradient descent, where you take all the examples. Here it's mini batch gradient descent. So you take the batch 64, and then you shuffle the data as well. So this simplifies preparing the data for you, the data loader object from PyTorch as well. And then you define the object, simple neural network, the cross entropy loss, and then finally SGD, where you pass in the model parameters using model.parameters. These are all your weights and biases that we're going to update, and this is the learning rate. All right, and this is the typical training that you would go through. So you pass in an image and a label, and it loops through the train loader. This is the data loader where you loaded the data, and it does that one mini batch at a time. It sets all the gradients to 0 because PyTorch assumes that the gradients are accumulated unless you explicitly set them to 0. This has some useful use cases for large data sets. Then it does the forward pass, takes in the image, model gets the output, that's a 10-dimensional output, applies the criterion, which we defined as here is my cross entropy loss. So it calculates the loss between the actual output and the predicted output and gives you that loss, and then back propagation. That's doing the back prop, computing all the gradients through all the network using, if you remember, the computational graph in the background. And finally, it performs the optimization step that's actually updating the weights, and it adds the loss, the total loss at the end, right? So that's the running loss through all the examples or through all the data set. Right? And at the end, it just prints. So this is a very good summary of how you would build a neural network in PyTorch, a very basic neural network. And it's probably seen a ton of these examples, specifically with this data set. This is a very popular data set. Again, it goes through the details, forward pass, things we've seen before. So here you can see the more sophisticated type of backpropagation step. Actually, that's really impressive. I've been just reading through the answer of a very simple prompt. So DLDW1 is DL dy hat DH2, DH2 DH1, DH1 DW1. This is going through all the hidden layers. It's not explicitly going through the activation functions phi, which I think, actually, no, never mind. That's completely fine. And then it performs. So once you calculate this, you just apply the gradient descent step here. This should be W1. And it's actually stuck, so we can tell it to keep going. Well, it has a summary, so it doesn't really matter. All right, so this concludes a very simple example that next time I will input that code. I actually encourage you to do that first yourselves, and then you input the code. Let me see if I can do that now quickly. So let me take this. I'll copy it, and I'll go to the code. See, I had some code here before, so I'm going to remove it and replace it with this. All right, so so there was a problem with a restart. All right, so I restart and then I run again, and we'll see if it actually works. So again, this is how it's defining the network, loading the data, defining as the optimizer, the loss criterion, and then doing actually just 5 epochs. Typically you have thousands of epochs, and it's working. So here it's printing that for each epoch the loss is actually decreasing. All right, so this is it for this demo, and we'll see. If you like this approach, I'll send you more and more examples, and I'll show you how you can actually work with ChatGPT to learn more about things. So of course, if there's something you don't understand now in this demo, you can see how you can just simply ask it about it. What does this mean? Can you give me better examples? Can you show me the math? I think show me the technical details is what distinguishes you from someone who's simply using machine learning to someone who really understands the underlying theory. And I truly believe that you don't really need to take a university course to understand the underlying theory if you're simply curious about it. There's another thing that I recommend doing is to ask it to give you exercises for practice. Maybe I'll do that in a separate video as well. But for now, just take it from there, and hopefully that was useful. So